Good morning, students. Today I will explain the effect of input, that is type and magnitude, on steady state error. Steady state error is represented by ESS. So this is also nothing but a static error coefficient method. Okay. For example, the first one I'll consider reference input is step of magnitude A. Reference input is step of magnitude A. So here I have considered a step function. Okay, so that is represented graphically like this, which is having a magnitude of A, right? So this is to be a desired output, and I have considered the actual output, that is in the form of oscillatory, this is my actual output. This oscillatory waveform is indicating an actual output. The difference between desired output and the actual output is defined as a steady state error, that is E subscript SS, ESS. Okay, so as you know from last class, R of t is equals to, we can write A, R of t is equals to A, and Laplace transform of this can be written as R of S is equals to A divided by S. And from yesterday's class, you know that ESS, that is steady state error, is equals to limit S tends to 0 S into R of S divided by 1 plus G of S into H of S. This is the formula. So this formula we got from the derivation that we have derived in the last class only, in the last video, right? So substituting R of S is equals to A by S in this equation, right? So this S and S get cancels. Okay, so ESS is equals to A divided by 1 plus limit S tends to 0 G of S into H of S. Okay, so we'll remove this, we will replace limit S tends to 0 G of S into H of S by some constant. So that constant is referred as positional error coefficient. That means this entire term, limit S tends to 0 G of S into H of S, will be replaced by Kp, constant Kp, that is Kp is equals to limit S tends to 0 G of S into H of S. Therefore ESS is equals to what we can write? We can write A divided by 1 plus Kp. So this is for what? This is for reference input is step of magnitude A. Okay, so yes, for positional error coefficient is ESS is equals to A divided by 1 plus Kp, we can write. Okay, Kp is equals to, we can write limit S tends to 0 G of S into H of S. Okay, the second thing is reference input is a ramp magnitude of A. So we'll consider ramp function. Okay, and we'll consider again the actual output in the oscillatory form only. Of course, you know this is actual output and this is the desired output. So the complete sketch, the time, this is the time response that is represented by C of t only. Okay, so here you know for ramp input from yesterday's class, again R of t is equals to, we can write AT, and if you take Laplace transform, R of S is equals to A divided by S square. So again we know the steady state error formula, ESS is equals to limit S tends to 0 S into R of S divided by 1 plus G of S into H of S. Again R of S I'll replace A divided by S square. So S, 1 S from S square will get cancels. So we can write limit S tends to 0 A divided by S into 1 plus G of S into H of S. The same formula can be written as, after multiplying with S, after opening the bracket, this can be limit S tends to 0 A divided by S plus S into G of S into H of S. Okay, so ESS is equals to, as limit S tends to 0, this S will be removed. Okay, so it remains only A divided by, because in the numerator there is no S term, that's why this limit I am taking directly to the denominator. That's why ESS is equals to A divided by limit S tends to 0 S into G of S into H of S. Okay, so this limit S tends to 0 S into G of S into H of S is removed by again Kv, that is velocity error coefficient. Okay, so Kp is positional error, previous one, this is velocity error coefficient Kv. Kv is equals to, we can write limit S tends to 0 S into G of S into H of S. Therefore ESS is equals to, we can write A divided by Kv. This is the second one. And coming to the third one, that is reference input is parabolic of magnitude A. So we'll consider a parabolic graph. Okay, so with again oscillatory actual output. as you know, difference between actual output and desired output is ESS, steady state error. So from yesterday's class, again you know RT for this parabolic function, RT is equals to AT squared divided by 2. Okay, so Laplace transform of this is A divided by S cube. Okay, again you know the formula, ESS is equal to limit s tends to 0 S into R of S divided by 1 plus G of S into H of S. This is the steady state error formula. Okay, ESS is equals to, again we'll substitute the value of R of S, A divided by S cube. So this 1 S will get cancelled with S cube, so still S square remains. So in the next step, limit S tends to 0, A divided by S square in the bracket 1 plus G of S into H of S. Again, okay, in the next step you can also write, you can open the bracket. If you open the bracket, so here I have written directly, but if you want to make still easier, in the next step this is equals to limit S tends to 0, A divided by S square plus S square into G of S into H of S. Next step. Okay, so this single time S square will tends to 0 because S tends to 0. So next step we can write ESS is equals to A divided by limit S tends to 0, S square G of S into H of S, and this will be removed by acceleration constant. Okay, that is Ka. This will be removed by acceleration constant Ka. That means ESS is equals to A divided by Ka. So hence we can write Ka is equals to limit S tends to 0, S square G of S into H of S. Okay, so like this we can see the effect of steady state error, right, with respect to type and magnitude. Okay, and on this topic you will get more number of problems in the exam.